Accurately characterizing large viral vectors is indispensable for ensuring the safety, stability, and efficacy of viral vector-based gene therapies and vaccines. However, characterization methods are often time-consuming, requiring multiple orthogonal techniques. I'm Miles Skoda. This is the Life Science Connect webinar series, and today we're talking measuring viral vector purity, stability, and physical titer in minutes with just one tool. Now, joining me for this presentation is an industry expert from Refeyn, Dr. Laura Palla, Product Marketing Manager, who is going to highlight the advantages of macro mass photometry to characterize viral vector purity and stability, discuss how the KaritroMP can quickly assess the purity of adenovirus preparations, quantifying empty capsids and other impurities, and show how KaritroMP data correlate with the physical and functional titers of LV samples, and finally demonstrate how the KaritroMP can be used to optimize production and purification methods. Now, we'll be holding a Q&A session following this presentation, so please feel free to submit questions as we go along. We'll get to as many as possible during the Q&A, and any that we don't get to, we'll follow up on after the event. And then just a bit of housekeeping. If you run into any issues today, please try refreshing your browser first. If your problem persists, submit a question through that Q&A, and I'll help get you back on track. And then finally, this event will be available on demand, usually within a day or two. You'll get an email with a link to it, or you can just use the same link that you used today. So with all that said, I'm going to turn it over to Laura to get started.
Thank you very much for the introduction. I'm really excited to tell you today about the KaritroMP, this tool that can measure viral vector purity, stability, and physical titer. Just to introduce, this is the KaritroMP. It's a nice benchtop instrument that is used to characterize adenovirus and lentivirus purity and stability within minutes. Refeyn recently launched this machine, and I'm really excited to tell you more about it. So I will start telling you about KaritroMP for adenovirus characterization, and then I will move towards the lentivirus characterization information. So let's start with the adenovirus analytical challenges. When making adenoviruses, there are a series of particles, impurities, that are made together with the desired product. So the desired product is the full adenovirus, which are the only functional particles in there. And then you have a series of impurities that ideally should be removed. So you have empty adenoviruses, which decrease the drug efficacy, presence often of helper virus, which is associated with safety issues because it's immunogenic, so should be definitely removed, and a series of fragments and degraded capsids, which also decrease the drug efficacy. And that's why it's really important to quantify them so that they can be removed in the process. The analytical challenges when making and characterizing adenoviruses are the lack of fast in-process analytics that can rapidly quantify populations, such as the presence of empty, helper virus, and fragments. There are a series of analytics out there. However, these are often non-scalable, such as analytical ultracentrifugation or electron microscopy. They are unable to quantify impurities, such as physical and infectious titer assays. And also, they are unable to resolve populations, such as size measurements. Therefore, there is a real need for a tool that is able to quantify impurities in process. So let's look at more in detail to why it's important to characterize adenoviruses in process. The adenovirus manufacturing process is composed by a series of steps. So you have the upstream stages and the downstream purification stages. Looking more in detail into the downstream, you can see that you have a series of steps sequentially. Here is just an example of a series of steps that can be applied to a downstream purification for adenoviruses. Each of these steps will take several hours at least. Therefore, in-process analytics could help basically checking adenovirus purification after each and every steps. While doing that, you can monitor the percentage of impurity throughout the downstream purification in real time. So you can check whether the process is going in the right direction on the fly. You can take a quick decision on the next step. So you can decide whether it's worthwhile to troubleshoot with additional analytics. And by doing so, you can save time and resources because you have the chance to stop the process early if that's faulty. So Caritro allows you to not to wait essentially until the end of the process. You can measure the percentage of empty, full, and adenovirus as well as fragments after each steps, and this can save you hours or days if you find out that things are wrong earlier and can act on it. Now let's look at how Caritro can help. So Caritro can provide a single particle resolution easy technique without any sample preparation, and can measure samples in a few minutes each. It can resolve and quantify adenovirus populations such as empty, full, fragments, as well as Lentivirus, and allows for in-process automated analysis on small volumes and concentration. So this can help you answering a series of questions. For example, on drug efficacy, the presence of empties, as mentioned, can decrease the drug efficacy, and therefore a quantification of empty versus full can really help, especially when done in process without any sample prep. It can help answering questions in terms of product safety, because it can identify and quantify the Adenovirus population within minutes. It can help assessing the stability of the product, because it can look at comparison between different buffers and different conditions, and this can be done on up to 13 samples in parallel. And this means you can avoid to go blind. Effectively, you can monitor and optimize adenovirus purification process on the fly with this automated assay that only requires 2 hours from sample prep to analyze results. I would like to tell you a bit more about the technology that KaritroMP uses, which is called macromass photometry. So macromass photometry is an evolution of Refeyn core technology, mass photometry, and this has been developed to measure large particles, large objects. It's a measurement that happens at a glass-liquid interface, where you have a droplet of sample which is applied on a sample carrier slide. The particles are immobilized on the surface, taking advantage of non-specific binding. And what you do is you send a light source from below, and you collect the light which is scattered by single particles, which is interfering with the light reflected from the glass surface. This signal is called scattering contrast, and is related to the particle's mass and refractive index. So effectively what it gives you is a proxy for mass information for single particles, or if you prefer, an uncalibrated mass axis. In addition to that, we also collect another parameter, which is the particle height. So effectively, this is the vertical dimension of the particle on the surface. We do that by sweeping through focus, meaning we are moving up and down this glass light on top of the objective, and we again collect the vertical dimension of the particle on the slide. So this vertical dimension, this particle height, would correspond to the particle diameter if you have a rigid particle, spherical particle. However, if you have a particle which is non-rigid or non-spherical, this is only effectively the particle height per se, meaning that is related to both the diameter but also the inner cohesion of the particle itself. So at the end of the day, what macromass photometry allows you to do is the measurement of single particles with 2 parameters: the contrast, or proxy for mass, which again is the interference between scattered and reflected light, and the particle height, which is obtained by sweeping vertically on the glass light, and is a measurement of size. Now, looking more into detail into the information that the Caritro gives you, here we have an example in the left side of the slide. We have the measurement of the contrast and particle height together, represented in this plot. So you have the horizontal axis, so the x-axis representing the contrast distribution for single particles. The vertical axis, which shows you the size distribution or particle height distribution for the single particles measured, and then a scatter plot or dot plot in the center, where each data point would correspond to a particle measured there with a certain value of contrast and size. So here in this plot, we are showing a measurement of adenoviruses, where we have a mixture of fragments, empty and full. So we can see the various populations in there. So let's start from the fragmented capsids. These are represented in the gray rectangular area, the gray gate. They appear at the lowest value of contrast as well as size. Reason being because they are they have small size and small mass, considering that they are only fragments. Then we have two populations, one in the blue gate, which corresponds to the empty adenovirus capsid, and one in the orange gate, which corresponds to the full adenovirus capsid. If you look at the contrast histogram, you can see that the empty appears at lower value, compared to the full capsid. Reason being that, of course, it's lighter. It has a lower mass compared to a genome-loaded adenovirus capsid. But if you look at the size axis, the two of them fall under the same peak. They're not resolvable because effectively they have the same size. So here, actually, the value of the contrast axis and specifically of the Karitro is the unique capability of distinguishing and resolving populations based on their differences in mass rather than differences in size. And I'd like to emphasize this unique capability by looking at this data set in here, where we are measuring our size calibrant called sizeferns. This is a mixture of silica beads of different sizes, ranging from 50 nanometers to 120 nanometer diameter. So what we do is we mix them in an equimolar mixture, and we measure them with the KaritroMP. So if you look at the size histogram on the vertical axis, what you can see is that it's really difficult to resolve these populations because they have effectively similar size. However, if you look at the contrast histogram, you can really tell apart and resolve all the 5 populations from each other, even the 50 nanometers from the 60 nanometer beads, which is quite powerful. So in here, what we are showing is that effectively Karitro takes advantage of the mass difference to distinguish populations that have similar size. Now I would like to go through some examples of adenovirus data. In here, we are showing how the KaritroMP can be used to assess quickly adenovirus purity. So, as mentioned in the introduction, the Karitro can resolve empty, full, and fragmented adenovirus due to their max difference, which is expressed in the contrast axis here. So you can see again the 3 population of the fragments, the empty, and the full capsids. The presence of the empty and fragments was confirmed by SDS page. And here what you can see is a percentage of counts above the empty and the full gates with a standard deviation value, which can show you how the measurements are actually quite reproducible. So the conclusion of this is that the KaritroMP can be used to determine the percentage of empty adenovirus in samples within a few minutes. So the next steps after these initial experiments was to measure more complex samples. So here what we've done is we measure a ladder of empty-full mixtures ranging from 0% to 100% full capsid. This was done in collaboration with the Jenner Institute at the University of Oxford. And what you can see in these 3 plots is how the data appear for the various mixtures. So the first graph shows you how the theoretically 100% empty sample look like. And here you can see a presence of a major peak in the empty region and a small amount of full capsid, about 8%. The theoretical mix at 60% full shows you really nice agreement in what we measure. So again, 60.1% full capsids in the sample. And then the 100% full shows about 97% of full capsids when measured on Karitro. So we have a really nice agreement, and as you can see from the graph in the bottom, there is a very strong positive correlation between the theoretical ratio, so what calculated from the mixing, and what we measure with the Caritro. All data points were also measured within the 10% of the theoretical ratio, which is reassuring. But you can see a small offset in here at the low value, which is related to the fact that the empty capsid contains some pure in there, which is reflected in the first graph. That's why we have this small offset. So the conclusion of this experiment is that with the Caritro, you can reliably quantify an adenovirus empty to full ratio in minutes, and again on small sample amounts. So the next step to this was to compare how the KaritroMP, compare the KaritroMP with other analytical methods. So the ladder of empty-full mixtures shown in the slide before was analyzed using the Caritro, so macromass photometry, analytical ultracentrifugation, electron microscopy, and anion exchange HPLC. And you can see the data represented in this plot. So if you look at the dashed line, this is the basically theoretical values, and the orange line, which is the Caritro, shows that effectively this is the method that most closely align with the theoretical mixing. And there are small deviations with the other methods. I would like to point out also that the Caritro is significantly cheaper compared to AUC and EM, and much more precise compared to HPLC. Therefore, we can conclude that the KaritroMP is the fastest tool for a robust adenovirus empty to full ratio quantification. Now, I would like to show you how the KaritroMP can monitor adenovirus production processes. Here we have three fractions from a production process, the clarified, one of the elutions from chromatography, and the purified drug substance. So in the clarified sample, you can see that this is quite heterogeneous. You can detect the presence of empty and full capsid, but also a lot of other particles in other regions. In the elution 2, you can see about 89% of the empty capsids and about 11% of the full. And the drug substance shows about 71% of the full and 29% of empty. So what we are doing with the Caritro is measuring an enrichment of a full versus an empty adenovirus throughout the process, again on the fly, because this takes a few minutes per sample. So this is showing the power of Caritro that can give this assessment during the process on minimal sample amounts. Also here, I would like to show you how the Caritro can differentiate full adenovirus from the presence of helper virus. It is quite important to quantify the helper virus in adenovirus preps because the helper virus is immunogenic, so it poses safety issues, and therefore it should be quantified and removed in the final product. So if you look at this comparison in here, we have populations that appear at the same size for what concerns the full adenovirus and the helper virus, but slightly different contrast. The reason is that the helper virus contains a genome which is slightly larger compared to the full adenovirus, and therefore is a little heavier in terms of contrast. So there is a shift at larger contrast values. So if we gate the various region, for the full adenovirus, we detected 99% of the data point within the full adenovirus gate and less than 1% in the helper virus gate. If you measure the helper virus, you have 89% of the data point in the helper virus gate and about 11% in the pure adenovirus gate. So this is telling you that even though there is a partial overlap of the two populations in terms of contrast, the Caritro can really distinguish them and can relatively quantify presence of helper virus. Cannot really resolve them if the helper virus is present in trace amount, but we can still give a numerical assessment in there. And then I would like to show you how the Caritro can monitor the adenovirus stability. So what we've done here was doing a force degradation study. So we thermally degraded the adenovirus sample by heating up at 47 degrees over an hour time. So we are showing the difference between the, the sample kept under normal storage condition versus the sample heated up after 15 minutes and then after 1 hour. So in the stable sample, you can see that about 47% of the data point over the total are in the adenovirus region. After 15 minutes of thermal degradation, you can see that this decreases to about 18%. And you see the appearance of new population that are quite clear in terms of contrast as well as in the scatter plot, which are likely a degradation product. After 1 hour heating up, you can see that the adenovirus gate doesn't contain particles anymore, so all the adenovirus is gone, and you have the increase of this population at lower contrast. So Karitro effectively can be used to quickly assess the adenovirus stability, either for force degradation study or for shelf life investigation of this product. And the last slide I've got on the adenovirus on Karitro is a comparison between DLS, NTA, and Karitro itself. So what we have in here is an overlay of the 3 techniques on the size axis and, again, the usual contrast measurement on the horizontal one. We have a mixture of empty and full adenovirus, as you can see from the gates as well. And what we can do with Karitro, as mentioned earlier, is resolve them thanks to their difference in contrast. If you look at the size peak again, these basically is only one peak for the 2 populations that fall exactly at the same size. So the power of Karitro is the differentiation and the resolution of the 2 populations thanks to the fact that there is the contrast axis, so the difference in mass. If you look at the orange plot, the NTA measurement, you can see that there is a nice, well-resolved peak in the adenovirus region. However, this encloses both the empty and full populations underneath because effectively they are at the same size. In terms of broadness of the peak, is quite similar to what Karitro measures, but the size measure is slightly higher due to the fact that NTA measures hydrodynamic diameter, while Karitro measures geometric diameter, and therefore the values are expected to be slightly lower. If you look at the DLS data, which are the green one, what you can see is an extremely broad peak where, again, there is no possible resolution between an empty and full population. The poorer resolution of the DLS peak is due to the way the technique works and the fact that this is an ensemble technique, while NTA and also Karitro are single particles based. So the conclusion of this is that size measurement alone cannot really help detecting and quantifying an empty and full mixture, simply because they have the same size. And you need some other sort of differentiation. One of them is what Karitro does, for example, looking at mass differences, which is his unique capability. Okay, so now I would like to tell you more about how Karitro can be used for lentivirus characterization. And let's look at the analytical challenges first. So the particles that are obtained from lentivirus production are a mixture of functional lentiviruses, which are the only infectious particles with therapeutic effect, and a series of impurities, which are non-functional lentiviruses, which are lentiviruses missing certain components, meaning that they are not going to be infectious and they have no therapeutic effect. And then you have exosomes or extracellular vesicles, which are produced from the cells together with the lentiviruses and are quite difficult to get rid of. The analytical challenges here are the lack of fast in-process analytics that can be used to monitor the enrichment of the lentivirus product. There are assays, of course, out there. The gold standard is the infectivity assay. However, this is very slow because overall it takes several days and therefore is not suitable for in-process measurements, but only for the final product measurements. So the need here is a fast and robust titer estimate that can support process development and process monitoring. Let's look at more in detail why it would be advantageous to characterize lentiviruses in process. So again, here we have a nice flowchart showing the various steps in the upstream and downstream purification. This is just an example. Every manufacturer would have their own series of steps. However, what is definitely true is that each step in the downstream purification would take several hours. And if you had in-process analytic to look at each of these steps within minutes, you could monitor the lentivirus enrichment throughout the downstream purification in real time. So you can understand whether things are going in the right direction, and you can take a fast decision on the next steps, whether you want to troubleshoot with additional analytics or stop the process if things are not going right, saving time and resources. So this means that you don't wait until the end of the process to actually get an answer on what's going on during the manufacturing. And you could save potentially hours or days if things go wrong. So let's look at how Karitro can help here. Karitro provides in-process automated analysis on small volumes and concentrations. It is a fast tool that can monitor and optimize the enrichment of the lentivirus product on the flight. It can give a physical titer estimate with single particle resolution, no sample prep, and in a few minutes per sample. So the Karitro can help you answer several questions here. So, for example, is the process going in the right direction? Because you can monitor and optimize the lenti purification by looking at the lenti enrichment at every step. You can compare methods and understand which one gives you the highest lentivirus yields, and therefore you can better understand your process. You can make decisions faster by estimating the functional lentivirus titer and the quality of the prep within an hour instead of waiting until the very end of production and much more time-consuming analytics. And it allows you, again, not to go blind because you can quickly check the quality of your prep and then decide what to do next. So I would like to show you some data now. This is an example of lentivirus data on Karitro. As you can see, the graph shows a quite broad distribution of data points in there, quite a lot of heterogeneity. This is due to the fact that in there you have a mixture of particles. So you have functional and non-functional lentiviruses, you have extracellular vesicles, fragments, large protein aggregates, all in there mixed together. And Karitro, what it can do is identify what are lentiviruses from extracellular vesicles and also fragments and protein aggregates, as you can see in the enclosed lentivirus region. So, because of the heterogeneity of the sample in the lentivirus preps, it is important to define the exact location where you can find the lentivirus particles in these 2D plots. And we have done this study in collaboration with Professor Dirk Lendemann's lab from Dresden University. Here what we've done is measure a positive control, which is the blue graph, versus two negative controls, which are the following two. The positive control, again, is a lentivirus isolated from supernatant, and then the first negative control is coming from a mock transfection. The second negative control is coming from a transfection of the lentivirus genome and the VSDG plasmid, but without the packaging protein plasmid. So what you can see from these three graphs is the presence of about 11% of particles in the lenti region, but no particles for the two negative controls. So in here, what we can assess is that even though these samples are really heterogeneous, the KaritroMP has the power to distinguish lentivirus from the other particles. I'd like to show you how the Karitro can assess the lentivirus purity in process. So here we compared a crude sample with a purified sample. So in the crude sample, you can see about 2% of the particles over the total in the lentivirus region, and they increase by tenfold in the purified sample. This has a nice correspondence with the infectious titer that was measured by our collaborator, which increased by about sevenfold. So what we are showing here is that the KaritroMP can be used for a process monitor assessment because it can give you a purity information on the lentivirus enrichment throughout the prep within minutes. So the next question we had was, what can the KaritroMP tell us about the physical titer, which is what we are representing here. In order to investigate this, we've been measuring a series of samples with different titer values. So we have a negative control in the first graph, a sample with low titer, and a sample with high titer. And what you can see is that the Karitro analysis shows a higher lentivirus percentage for the samples with a high titer versus the low titer. So the conclusion was that the KaritroMP can be a tool for rapidly measuring physical titer, but let's look at the correlation more in detail in the next slide. So in here, what we are showing is how the Karitro data correlate with the physical titer. So we tested 12 samples with a broad range of physical titers, and what we are showing is on the horizontal axis the percentage of counts in the lentivirus region measured on Karitro versus the physical titer measured by our collaborator on the vertical axis. And what you can tell from this is that there is a really nice positive correlation between the two methods, because effectively the KaritroMP can be used as a rapid estimation tool once the specific titer assay is known. And again, let's remember that every measurement would take a few minutes per sample. So the next question was, what about functional titer? Do the Karitro data correlate? We've done pretty much the same experiment, but what we are comparing here is the Karitro counts versus the functional titer assessed by flow cytometry. And what you can tell is that there is, again, a positive correlation here, but due to the fact that the Karitro is insensitive to functionality, the non-infectious particle fall out of the trend. The positive aspect here is that in a few minutes you have a clear distinction between infective particles and negative controls. So the conclusion is that Karitro can be used for a rapid titer estimate at every step of the process, and this can help decide what to do next. So does it worth my time to perform a time-consuming infectivity assay or not? So I'd like to tell you a bit more about the consumables that the Karitro uses, as well as the workflow. So in terms of consumable, we provide a KaritroMP sample carrier, which is composed by 3 components: a slide, a mass glass KV slide, which has been optimized in terms of surface for viral vectors characterization, a 14-well cassette, which is this silicon component there with 14 wells, which allows to measure up to 13 sample and 1 calibrant, and then a lid in there. So the advantage of this design for a sample carrier is that it is a closed system, so it can facilitate the handling of these samples in a BSL2 environment. So for example, you can load the sample carrier under a biosafety hood rather than on the instrument directly, reducing the risk of exposure for the operator as well as contamination on the machine itself. It allows for an automated workflow where you can run up to 13 sample and 1 calibrant. And it requires very small amounts of samples, because we would need only 5 microliters of a sample at 10 to the 8, 10 to the 9 particles per milliliter, which is a really low concentration. The time to result, again, is really fast. It's about 1.5 hours from the beginning of the run until the production of the results. The other consumable needed for the Karitro measurements is the size-friends, or the KaritroMP calibrant. If you remember, I showed you this data at the beginning of the presentation. This is used to calibrate effectively the particle height axis into nanometer. And I would like to dig a bit more into the workflow. Karitro uses an automatic acquisition workflow that is composed by a first part, which is hands-on, followed by an automated portion. So for what concerns the hands-on part, what you need to do is the sample prep, so dilute to the appropriate concentration, load that into the sample carrier by basically pipetting, placing it on the instrument. You need to set up the software, basically saying which sample is contained in which well. And from that moment, the instrument goes on its own without any need of operator input. So the 14 wells are run automatically, and the results are produced on the fly. So after 1.5 hours run, you come back to the machine, and your data are ready to be exported, already analyzed. So in terms of macro mass photometry benefits, definitely the limited sample prep is one of them. It's a label-free measurement on particle in native state. It only requires dilution to the appropriate concentration, but that's it in terms of sample prep. It's fast because it takes a few minutes per measurement, including the analysis. Or if you run a full cassette, it would take you about 2 hours, including both sample prep and data analysis for 13 sequential samples. It requires a low sample amounts. So we are talking about 5 microliters, around 10 to the 8, 10 to the 9 particles per milliliter. It's quite easy to use. There is no method development. Training new users independently on their background takes about 1 day. So it's quite user-friendly. It has a really small footprint. It's a benchtop instrument. And the operational costs are really low. So we are talking below $5 per measurement. So in conclusion, I hope that I convince you how the KaritroMP can be a really convenient tool for adenovirus and lentivirus purity and stability assessment. It's fast, can be used in process, gives you information on the various populations present in there, and can help you identifying issues with the process so that you can ideally stop it sooner if there are any issues. So yeah, thanks very much for your attention, and I'm happy to take questions.